everyone, we are Group 11 from Division O, from roll numbers 59 to 64. We will be explaining floating point representation. The IEEE standard for floating point arithmetic, that is IEEE 754, is a technical standard for floating point arithmetic established in 1985 by the Institute of Electrical and Electronics Engineers, that is IEEE. The standard addressed many problems found in the diverse floating point implementations that made them difficult to use reliably and portably. Many hardware floating point units use the IEEE 754 standard. A floating point format is specified by first a base B, which is either 2 binary or 10 decimal in IEEE 754. Second, a precision P, and third, an exponent range from Emin to Emax, where Emin equals to 1 minus Emax for all IEEE 754 formats. Next, it has three parts: mantissa, base, and exponent. In the 32-bit, that is single precision representation, the first bit represents the sign bit, the next 8 bits represent exponent, and 23 bits are the mantissa. In 64-bit, that is double precision representation, the first bit represents the sign bit, the next 11 bits are exponent, and the next 52 bits are mantissa.
Single precision floating point format. Single precision floating point format is a computer number format usually occupying 32 bits in computer memory. Double precision format. Double precision floating point format is a computer number format usually occupying 64 bits in computer memory. Moving on to the steps to convert a decimal number in single precision or double precision format. Convert the decimal number to binary number. Second, normalize the number. Third, if it is a single precision format, then it should be into bracket 1.n bracket complete 2 raised to e minus 127. If it is a double precision format, then it should be into bracket 1.n bracket complete 2 raised to e minus 1023, where e is the exponent and n is the fraction.
Next, we will learn an example about single precision format. The example is as follows: 263.3 to the base 10. Firstly, we will convert the number to the binary form. For this, we will firstly take 263, the whole number, divide that by 2 until and unless we get a remainder 1 as 0. You can see that in the picture which is on the right side. We divide 263 by 2, on which we get 131 and the remainder is 1. Then we divide 131 by 2, on which we get 65 and the remainder is 1. And we do so until we get remainder as 1 or 0. You can see that on the right side. And then we consider the binary form of 263 from downwards to upwards. So the number becomes 100, 000, 111 to the base 2. This is because we divide 263 by 2. Simultaneously, we convert the 0.3, which is the decimal, to binary form. This is done by multiplying 0.3 by 2. We multiply 0.3 by 2, on that we get 0.6. Here 0.6 is the decimal part and 0 is the whole number part. Then we just multiply the decimal part with 2 again, and on that we get 1.2. Here 1 is the whole part and 0.2 is the decimal part. So simultaneously we only multiply decimal part with 2, and when the numbers start recurring again and again, so, we will stop the multiplication, and we will consider the binary form. We will consider the binary form for decimal part from upwards to downwards. So we write 0 1 0 0 1 1 0 0 1 1 0. Then we consider the whole binary form for 263.3 to the base 10. This is written. Firstly, we write the binary form of 263 point, the binary form of 0.3 to the base 2. Then we normalize the number. For normalizing, we multiply it with 10 to the power 8. This is because we have to shift the decimal by 8 8 points. Next, for single precision format, there is a formula which is 1.n into 2 raised to e minus 127. Here e is the power of the number 10, and here we find the value of e, which is 135. Then we find the binary form of 135, which is 100 00 111 to the base 2. Then we represent in this format, which is given below. The first bit is sign bit, the second is exponent, then is mantissa, and we get the answer.
Now next, double precision format. Same example as previous. First step, convert given number into binary form. So binary of 263 is 100001111. This all calculation is done before. So next, binary of 0.3 is 0100110. So overall binary of 263.3 is 100000111.0100110. So next step, normalize the number. To normalize this, we have to shift this point to left by 8 decimal point. So binary of 263 is given by 1.000 and so on into 2 raised to 8. Now next, for double precision format, we have 1.n into 2 raised to e minus 1023. So comparing with previous, e minus 1023 is equal to 8. So e is equal to 1031. Now we have to convert 1031 into binary. 1031 is 10000000111. So to represent this in double precision format, first one bit is to sign bit, and this our result is in exponent, and this is mantis.
One more example, that is 1259.125 to convert into the represent into the floating point representation. First convert it into the binary form. As we see before it, it converts 1259 to binary form by dividing 2. If it is totally divisible, then remainder is 0, and if it is not totally divisible, remainder is 1. And by taking down to up, the binary form is obtained. Then next point, 0.25 also binary point here is given binary form, and then normalize the number. Count the number of digits from here: 1 2 3 4 5 6 7 8 9 10 11. But it is the first sign bit, so it does not count 11, so it 10 content, so it is here 2 raised to the power 10. So next, single precision format, we have to given 1.10 to raised to the power e minus of 127. Then 1 e minus 127 is equals to the 10 from here, 10 from here. Then e equals to the 137 binary form is this converted by this method, and this representation is given. One is for sign bit, exponent bit 8 bits, mantis are 23 bits, and this is given. 0 means 0 then denotes that the number is positive. This is the exponent, that is 137 by in binary form, and this is the number 1259.125, and remaining are because of it is 23 bits, remaining given as 0.
Now let us consider next example of double precision format. First consider the number given here, that is 1259.125. Now the first step will be to convert it into binary form. We can convert the number into binary form with the help of steps given here. First we will consider the number before the decimal point, that is 1259. This number can be converted into binary with the help of steps shown here. Now we will consider the number after the decimal point, that is 0.125. We can convert this into binary with the help of steps shown here. Now after performing these two tasks, we will get the binary form of the complete number as shown here. Now the next step will be to normalize the number. Normalizing the number is nothing but multiply the binary form of the number in with 2 to the power something, so that the decimal point in the binary format is shifted such that the decimal point will occur just after the first bit in the binary form. Now according to the IEEE standards, we know that any double precision format in floating point representation is given as 1.n into 2 to the power e minus 1023. Now we can see that our given binary form is in the IEEE 754 standards, so that we can interpret the value of e minus 1023 as 10. Now after solving the equation, we will get the value of e, that is 1033. Now the next task is to convert the value of e obtained, that is 1033, into binary form. Now the last, now so that we have completed our all further step for all initial steps, so we will perform the last step, that is to represent the number like IEEE as preferred by the IEEE 754 standards. The first bit will be the sign bit, the next 8 bit will be the binary format of the value of e which we have obtained, and the last 52 bits will be of the number, that is n, that we have obtained, that we can see here after the decimal point. Now the to so as to complete the 52 bits, we will have to add a number of zeros, so that the total count of the bits is 52. This is the final representation in the flow. This is the final floating point representation according to the IEEE format. Thank you for watching our video.